Hello everyone. In this video we're going to continue talking about hydraulic fracture design and physics. In a previous video we talked about the couple problem of fluid-driven fracture propagation, and we limit our discussion to simple models in which the fracture height was fixed. Today we're going to see what are the factors that affect that fracture height, and also how we can determine fracture height based on stress logs, or also what are called geomechanical models. So let's go into that. The main limitation of the previous models that we saw, like the PKN, the KGD, or the radial models, are that they are simplified models that assume some geometry of the fracture that usually in reality doesn't happen like in our assumption. For example, in the PKN and KGD models, the fracture height is constant and predetermined. In the radial model, the fracture height and the fracture length, they are the same and they increase simultaneously. However, in real fractures, as we can see on the right, we can have a fracture height that varies depending on the conditions. And also, before we can apply either the PKN or the KGD model, if we were to apply those simplified models, we will have to determine what that fracture height is. In this example, you can see what are called layers with low contrast, and that refers specifically to the minimum principal stress, in which the minimum principal stress almost doesn't vary as you go deeper. And in that condition, you will have a hydraulic fracture that if it starts growing something in the center, it's just going to grow symmetrically, similar to the radial model, and it's not going to find a clear boundary that defines a fracture height. On the opposite, in this case on the bottom, you have a case in which there is a high stress contrast. And that means that as you go deeper, there is a region, this formation, the red formation, in which the stress is lower than in the adjacent formations. That's going to cause that the fracture concentrates in the red formation. Why? Because the minimum total stress is lower than the adjacent formations, and the hydraulic fracture is going to prefer to grow in that region with the low stress. And therefore, the hydraulic fracture height is going to be related to this region of low stress, which in this case corresponds to this red formation. All right, so let's see how we can determine such variation of minimum principal stress, which is going to help us to determine fracture height. And the reasoning is relatively simple. Let's imagine that we go into the field and we run a wireline logging tool, and we measure the mechanical properties of a formation by measuring travel times. And let's say that in a region we have the delta P that is more or less constant, and at a given depth it increases. And we run this with this same wireline tool. We run also the logging tool for shear waves, and it shows something similar, that there is a region in which this travel time increases. So this is going to be delta TP, and this is going to be delta TS. If we were to interpret that log, we would infer that the formation in the middle is a softer formation than the adjacent formations. So this might look something like this. Let's extend these bed boundaries, and here we're going to convert that into an actual formation in which, let's say that I have a carbonate that it's very stiff on the top and on the bottom, and in the center I have a sandstone which is softer than the adjacent formations. Remember that velocities are inversely proportional to slowness. So if we had such formation, we could utilize the travel times and velocities in order to build a mechanical profile of the formation. And we're going to quantify this to what is called the plane strain modulus, which is equal to the modulus divided 1 minus Poisson ratio square. This is the plane strain modulus. And if we were to use here the theory of linear elasticity, we're going to see details about how to do that. We will compute this plane strain modulus, and this will show us that the carbonate is going to be stiffer than the sand, and this is going to look something like this, where the higher the plane strain modulus, the stiffer the formation is. And if we go one step further and we apply the equations of linear elasticity in order to determine what are the horizontal stresses, using the equations that we have seen before, I'm going to remind you here what those equations are. Just one sec, I thought I had that somewhere. This is in the chapter 3.34. And here, based on linear elasticity, we can predict what are the horizontal stresses, assuming that we have tectonic strains. As you can see, these stresses are going to be proportional to the vertical effective stress, but are also going to be proportional to these tectonic strains and to the plane strain modulus, and also it's going to be a function of the Poisson ratio. But the main idea is that the bigger the tectonic strain, the higher the stress is going to be. So let's say that in this case, we apply a tectonic strain that it is the same in the entire interval. If that tectonic strain is the same, this is going to mean that the stress is going to be proportional to the stiffness of the rock. So just to make this, to write it as a simple equation, stress is going to be proportional to strain. And therefore, what I'm going to have is that my horizontal stress is going to be higher in stiffer regions and is going to be lower in softer regions. I obtain this variation of horizontal stress with depth with this equation which is on the right, and you can modify your model to make it more accurate depending on your particular conditions. But the main idea is to have a model that allows you to quantify what is the stress based on tectonic strain and some other properties of the rock. But the main idea here is that now, if we know the properties of the rock, we know how stiff the rock is and what is the tectonic strain in that place, we can calculate what is the variation of horizontal stress with depth. And in this case, let us assume that this is under normal faulting conditions, so that the horizontal stress is the minimum principal stress, and therefore let me say that this horizontal stress SH mean, here I'm going to just write that S3 is applied in horizontal direction. If we were to have a hydraulic fracture that grows in this formation, it will look something like this. Let's say that it starts at the point over here. That's the point that we have our perforations, and let's say that this is our wellbore. Then this fracture would start growing as a radial or penny-shaped fracture, as the one that we were seeing before, and it's going to grow out. Now I'm drawing this growing out of the plane, okay? And it's going to grow in this direction, and more or less now the stress is all the same, so it grows. Let me add some axes over here to help me describe what I'm drawing. Let's say that this is X, Y, and Z. So the fracture is now growing in the plane XZ, and it's growing in direction X, and it's also growing in direction Z. The stress is the same everywhere, so for the fracture, it feels the same stress in all directions, so it's just going to grow radially until it hits the stiffer formation. Once it hits the stiffer formation, because we have higher stresses on the top and bottom formation, the hydraulic fracture is going to prefer to continue growing just on the formation in the middle. And that's what is going to determine the fracture height. So if I were to draw how that fracture is going to continue growing, it's going to continue growing, propagating the plane XZ, and it's going to grow like this. And as we were saying, it grows in direction X, and when it was small and the fracture length was smaller than the fracture height, it was also growing in direction Z, but now it's growing mostly in direction X. And because it cannot, let's assume that it doesn't go over the limit of the difference in stress or stress constant, this is going to be the fracture height. So based on the variations of stress, we can tell where the fracture is going to propagate. And this is something very important, because if you remember, we said that a hydraulic fracture is going to propagate always perpendicular to the minimum principal stress. And now we're adding one more thing, which is that the fracture is going to propagate always in the regions of the lowest value of the minimum principal stress. In real formations, this minimum principal stress is not going to be homogeneous, and it's going to vary with depth and also with horizontal distance. In this particular case, that sweet spot of low horizontal stress is in this location and is limited by these two stiff boundaries, and that's why it remains in this location. And you may wonder, what is the maximum pressure at which this fracture is going to jump into the next formation? This is going to be related to this difference over here. My net pressure could go as far as this difference, because in always that I'm in those conditions, the fracture is going to prefer to open up against this stress than against that stress. But when the net pressure at the wellbore is too high, because as if you remember what we said for the other models, in order to have the fluid moving in the fracture, in order to have a fracture which is open, in order to have creation of new fracture surfaces at the tip, your net pressure has to be positive, and there has to be a finite value. If that net pressure is too high at the wellbore, then there might be a chance in which your net pressure is going to be higher than your stress contrast, and then your fracture may continue propagating into the adjacent layers. For this particular case, let's just keep it like this, and in this simple case, this hydraulic fracture height will be determined by this sweet spot of low minimum local principal stress, as long as the net pressure is not higher than that difference in stress. All right, so now we know how to determine a fracture height based on a geomechanical model. And we also said that this fracture height could change with time when we overcome this stress contrast. And that's what a hydraulic fracture simulator does. In our previous models, we found analytical equations for constant fracture height or for this simple radial model because the fracture geometry was simple enough that we could solve it with these analytical equations. If we consider that fracture height it's a variable, then we cannot make those simple solutions anymore. But we can solve this numerically with a hydraulic fracture simulator. And this is what hydraulic fracture simulators do. Let me show here one example in which we have the snapshot of the simulation of a hydraulic fracture. Here you can see we have the stress log. We also have permeability and a third variable. And apparently this one is a simulation done with a software called fracpro. What you see here is the fracture here in the middle with a model which is not calibrated. So this will be the fracture height. This will be the fracture length. And after they calibrate the model, they limit that fracture height to the pay formation. And also that means that for the same volume, you will have a longer fracture length. But basically what you have to do is just to put this information about the formation in terms of mechanical properties and a calibrated model to tell you what stress is as a variation of depth. So your fracture simulator can simulate these fractures. Something else to notice over here is that, as you can see, this fracture is not symmetric, but the fracture width also varies with depth. Let's see something a little bit more complicated, but with the same principles. Here we have an example of another fracture simulator, which is called gohfer, and I'm going to zoom up into this fracture. And now we have horizontal wellbores. We're going to get into horizontal wellbores and multi-stage fracturing later on. But for now, let's just concentrate and let's try to see one fracture at a time. And for example, let's look at this fracture over here. What we see is that next to the wellbore is where we have the biggest fracture height that is related to the fact that the net pressure at the wellbore is the highest. But as you go further away from the wellbore, your fracture height is not constant and it decreases. Why? Because the net pressure, it gets lower as you get to your fracture tips. So what the hydraulic fracture simulator does is to put all of these factors together into a simulator that also has these variations of stress into a 3D geomechanical model that can tell you what is the variation of total minimum total stress with the location, and also what is its direction. And let me see if we find some other nice example over here. I think this is a nice one. Here, what you see in colors, it's either it's a fracture width or it's a propan concentration. That's what is usually plotted in these kind of graphs. And what you see is, again, something similar to what we were saying before, how the fracture width and fracture height are the highest next to the wellbore, but when you get to the tips, this fracture height tends to be smaller. And in this case also you can see how this hydraulic fracture in some way goes into two different formations. So in these two formations, the hydraulic fracture is looking for the formations of the lowest principal stress, and which in this case appear to be these two layers, and the one in the middle would be a layer with a high a minimum principal stress, and why this is not propagating in this formation. Of course, in this case, just to complete the picture, the direction of the minimum principal stress is in the direction of the horizontal wellbores. That's why our fracture planes are perpendicular to the direction of the wellbores, which is the direction of the principal stress. But in summary, what these hydraulic fracture simulators are doing are what we have been seeing so far. First of all, computing net pressures and fracture widths as a function of the rheology of the fluid, the properties of the formation, put it all that together, and now couple with the determination of the hydraulic fracture height as the fracture advances, and which is not constant anymore, but varies. And I have one more nice example to illustrate this concept, and this is about a recent software developed by a colleague of mine, Mark McClure. And in this simulation, what we're going to see are the growth of fractures as a function of time. So this is a nice animation. Let's start from the beginning. The lines are let's see if we can go full screen over here. The lines are the horizontal wellbores, and here you have different variables like pressure, aperture, propant, and in this case gas saturation. And we see that we have several fracture stages. In each of these stages we have perforations, and our fractures are growing out of this stage. And we can see here with all these variables how these fractures are starting to open. Let me go a little bit more in time. We see how these fractures are growing, and let me stop right here. Something very important that we see in this simulation is that the growth of fractures is not symmetric. It's not symmetric with depth, and it's not symmetric also with horizontal location. In this case, it is symmetric with horizontal location, but in general, it might not be. Here, we can appreciate the asymmetry in height. Like, for example, look at this Mickey Mouse head. You can see that in this case, this fracture and also the adjacent fracture is preferring to grow up rather than to grow down. The reason for this could be that the lowest principal stress and this particular location, it's lower in the top formation rather than in the bottom formation. Or let me say in other words, in this region of the wellbore, the stress is lower above the wellbore than below the wellbore. That's why the hydraulic fracture starts growing in this direction. And we also, you can tell me now, but look at this other fracture, it's growing down. Okay, this is caused by something which is called stress shadow, which means that if a fracture starts growing in a given location, it might induce a higher stress in this location, so the next one that tries to grow immediately adjacent to that is feeling the stress of the next fracture, and that's why it's not propagating in this location, but rather it's propagating downwards. All right, let's continue simulation. We're going to talk more about fracture stress shadows later on, but here we can see how the hydraulic fracture propagates and also how the growth is asymmetric. And This is why it's very important that we do not assume in real hydraulic fracturing treatments that hydraulic fracture height is a constant. We can see very clearly in this simulation how the shape of the hydraulic fracture is not constant. Hydraulic fracture height is not constant, and also the geometry of this hydraulic fracture is varying with depth. And again, this is related to the variation of total principal stress with depth, and also variations that may be induced by the presence of new fractures. All right, so all of that, it's incorporated through these geomechanical models. And let's see one more case that it's important to discuss. If you remember, when we were talking about dikes, we talked about the presence of a seal. Let me go quickly back to that. Right here. Let's look at this example. All right. These type of seals are hydraulic fractures that grow horizontally. And let's see how we could explain that based on variation of stresses. Let's say that we build a geomechanical model like this one, but now we put together all the stresses, the vertical stress and the horizontal stresses, such that this looks something like this. This is going to be stress, this is depth. Let's say that the vertical stress is going to increase with depth. Here in my plot it looks more or less constant, and the minimum principal stress, SH mean, I'm going to draw that like it's varying. We're going to say that there is a tectonic strain, and it looks something like this. And the maximum principal stress, let me do it in blue, it looks something like this. So in this case, we'll be on different stress regimes according to depth. We are going to a place in which the minimum principal stress is horizontal, and in this case this will be strike slip, and as we go up this is switching into reverse faulting. And the effect of that is that if we had a hydraulic fracture that, for example, grows into this formation, this could be caused, for example, as we were saying before, by the presence of a stiff layer. And let me make a schematic of a formation. If we have a hydraulic fracture that starts growing somewhere over here, I'm just making here the 2D plot, and propagates, we know it's going to grow in this region because, and it's going to be vertical because the minimum principal stress is horizontal. But when it reaches now this layer in which the minimum horizontal stress is now vertical, this is going to switch. And now this hydraulic fracture is going to start propagating horizontally, because now the minimum principal stress is vertical and it's not horizontal anymore. Let me write this down. So in strike slip, S3 is SH mean. In reverse faulting now, S3 is equal to SV. And this is what is called normally a T-shaped fracture. And you can find those when you have these types of rotation of stresses. All right, so these are the basics of determining what is the stress variation with depth with a given geomechanical model and with a given assumption of how tectonic strains and rock properties affect stresses. And we have seen what is the effect of that in hydraulic fracturing, and that's something which is very important. And that's what hydraulic fracture simulators use in order to predict the propagation of hydraulic fractures. So let's see now, I have summarized all of this into a workflow that allows you to determine that variation of stress. So in order to build this geomechanical model, this is the simplest solution to the problem. As we were saying before, we can run a wireline log, measure mass density. With mass density, we know that we can measure what is the total vertical stress. If we, in addition to that, run the sonic tools, we can measure the P wave slowness, the shear wave slowness. With that slowness, together with the density of the rock, we can calculate what are the elastic properties of the rock. And here you have the equations. So with VP and with BS, you can calculate what is called the dynamic Young modulus and the dynamic Poisson ratio. With those two, you can calculate the plane strain modulus, and there is one additional fitting that we do here. Usually, the elastic moduli that we measure through waves are higher than the actual elastic moduli that we have under quasi-static conditions. You know that waves, they apply a very small strain on the rock, and the hydraulic fracturing imparts a strain which is much higher than the one imparted by waves. As a result, the static Young modulus, which is the one the hydraulic fracture feels, is lower than the dynamic Young modulus. So we have an additional conversion factor, FDS, which is lower than 1, and which allow us to convert the values that we measure from wave propagation, either in a wellbore or in the laboratory, to static conditions. Usually this value is about 0.6 to 0.7. And once we have those two, now we can calculate what are we already knew what is a vertical stress. Now we can calculate what are the stresses as a function of depth. But there is a catch here. In this particular model, we are assuming that it's a linear elastic and it depends solely on the tectonic strain. If you remember, we said that using this equation and knowing what are the effective stresses, for that we require pore pressure too, and if we knew what the elastic properties are, and if we knew the tectonic strains, we could calculate what the effective stresses are and then convert that to total stresses. The catch is that we do not know what those tectonic strains are. And in order to get to know or to calibrate our model, what is done is to utilize data like from hydraulic fracturing tests, like a mini frac test, a DFIT test, a leak-off test, the ones that we have seen before, in order to calculate what the minimum principal stress is by varying those tectonic strains. And we can also use breakouts in order to calibrate what the maximum horizontal stress is for a vertical wellbore. If you remember, the breakout angle in a vertical wellbore is a function of the properties of the rock and the value of the maximum horizontal stress and the minimum horizontal stress. So with those two, with data from the well bores like breakouts and hydraulic fracture tests, you can calibrate your model and you can back calculate what your tectonic strains are in order to explain your field data. And with all of that together, you can build a model that can allow you to see what is the variation of stress with depth and how that is going to affect hydraulic fracture propagation. All right, so here you have another example about hydraulic fracture height. Again, you can see how hydraulic fracture height is it's a variable, and also actually hydraulic fracture length is a variable. It depends with depth. And also you here see a cross-section of a hydraulic fracture for the prediction of the width, which is also a variable. Putting all these variables together and this variation of stress with depth is going to allow you to make these calculations. And in order to do this, what you will need is a numerical solution that can be done through a hydraulic fracture simulator or to some code that you can write on your own. All right, so in this video, I'm not going to explain the details about how to build this geomechanical earth model or stress log, but in the separate video for the problem solving part, I'm going to do that.